Okay, an open plastic has a diameter of that. Placed on the table, the uniform magnetic field is directed upward and oriented 27 degrees from the vertical, encompasses the bottle. What's the magnetic flux through the plastic of the soda bottle? Okay, well, this is kind of a magnetic flux is the same as basically just like electric flux. As far as what it is, it's any sort of flux is always integral of whatever you're doing.
I think next time I register a cattle brand, I'm going to put flux.
Yeah.
Nobody else can do that. I am the old.
F.dA. Right, and that's for electric flux or magnetic flux or whatever. Well, so here's something that Cindy also needs to know. It's really simple though. So let me brush this. So Gauss law. Oh, don't do this to me. There we go. So Gauss law for magnetic fields, which this will actually help you on the last question on your test. Because the last question is explain why Gauss's law should be true. Okay, so remember what Gauss' law said. If you have some closed surface and you're counting the flux lines going in and going out, well, basically, whatever goes in has to go out. So it's always going to be zero. The only case where that doesn't happen for electric fields or whatever is like, well, let me step away from electric fields for a second. You think about like sinks and faucets or whatever. Like if you've got a faucet inside that region pouring extra stuff, then you're going to have more coming out than what's flowing in. Same thing if you've got a sink inside that region that's draining stuff off, then you're going to have less coming out than what was coming in because some of it's being siphoned off to this extra place. So that's kind of intuitively why Gauss' law is true. It's like the positive charges inside the region are like your faucets that are pouring out extra field lines. And the negatives are like your sinks that are sucking up the field lines coming in. Well, what about for magnetic fields? As near as anyone can tell from over 100 years of looking for them, no one has ever found a magnetic monopole. So, I mean, like the two ends of a magnet, you can kind of think of the positive and or the north and south, like the positive and negative charge or whatever. But all of our experience is anytime you have a north pole of a magnet, it is always attached to a south pole. So if you start counting all the poles inside of a closed region, well, there's going to be some positive ones, which are like your faucets, and some negative ones that are like your sinks. But there's always the same number of them. And so anything extra being poured in is also being sucked out. So for a magnetic field, the total flux through a closed surface is always zero because there are no magnetic monopoles. Now we're all sad because there are no magnetic monopoles, aren't we? This is, whoa, I was trying to move myself down. This is where if I was in trig, Angel would start singing that 1 is the loneliest number. He sang that several times already this deal. Okay, so like for this one, we got a soda bottle. There we go. So here's my soda bottle, and I've got a cap on it. It's actually asking us what's the flux through the bottle part of the bottle. But anything that comes in or goes out, I mean, has to be the same as the flux through the cap, because like whatever comes into the bottle part of the bottle has to flow out through the cap, or else it flows out through the bottle and it's canceled anyway. So what we're actually going to find is just the flux through the cap, and then negative that has to be the flux through the bottle. All right, so let's do that real quick. The opening diameter of that, uniform that, is directed upward and at 27 degrees. So all we need to remember, hey, what's flux? Flux is the field times the area times the angle between the field and the normal vector. So, and that's what they give us, because they give us it's 27 from the vertical. So, I mean, here's the top of the bottle. The normal vector is straight up. The field is 27 off of the vertical. So it's just going to be the flux through the thing is just the area times the field times cosine of 27. All right. So again, remember that flux for anything is always the field times area times cosine of the angle between the normal and the field. So, all right, cool. So we can find that really easy because we're awesome. All right, so the field is, well, let's find the area right quick. The diameter is that, so the radius is 0.0135 squared times pi. So there's the area times the field, it's 1.85. Then times the cosine of the angle, so 27 cosine is 9.44 times 10 to the minus 4th. And I probably should think about the sign. Nope, it wound up being possible. It's okay. Cool. By the way, WB is the unit for magnetic flux, which is a Weber. It's spelled like Weber. I'm not sure that this program is doing any better than the other one was. Okay. So that was a great idea, but it doesn't help.
Well, we can see your mouse moving, it just wasn't right enough.
Yeah, that's the thing. Okay, that's working right now. So WB is the unit for flux, and it's a Weber. Okay, cool. This day has really just not gone the way I intended it to. Let's get something from the end, and we'll call that good for homework 5. All right. We need to get on to 6. All right, we've got a rectangular loop of wire with the width of that and that parallel to a magnetic field. The loop is what torque acts on the loop. So we did one just like this for the college people last time. Basically, when you've got a loop inside of a magnetic field, well, what's going to happen? So here's a loop. But think about the right-hand rule. Let's say the magnetic field's going that way. Well, if I do the magnetic field on the right-hand side there, well, actually, let's make them all non-zero. Let's say the magnetic field is going like into the board. All right. So hand, palm into the board, the force is that way. But on the other side of it, hand, yeah, because the current is turned around, it's pushing the right side to the left, it's pushing the left side to the right, so nothing happens. Same thing on top and bottom. Except, instead of saying it's like that, what if it's at a very slight angle compared to the magnetic field? Now, if I push the right side to the left and the left side to the right, the whole thing is going to turn. So when you have a loop inside of a magnetic field, there isn't a force, but there usually is a torque on it. And you think, okay, well, what is the formula for the torque? Well, if you just, it's got to depend on the current. That's going to be one of your things. It's got to depend on the area of the loop. So, and the other thing, if it's like everything else in physics, it's either going to be a sine or a cosine. So the only question is, oh, which one should it be? Well, when it was flat like that, so the normal vector was the same direction as the field, I got 0. So which one gives me 0? Which one, if the angle is 0, you get 0? Sine. So apparently it's, the torque is,
What's the sign for torque?
it's a tau. It's those. There's a good looking tau. It's the current times the area times sine of theta, where theta is the angle between the normal vector
And the I is,
the I is current.
that's what I thought.
Yeah. So if we go back to the problem, so you can find the area. Okay, they give you everything that you need. So here it says that it's parallel. The loop is parallel. So the loop's in the same direction as the field, which means the normal vector is at 90 degrees. So the sine is going to be 1. So all we're going to have is just the area times the magnetic field times the current. Oh, I left out the magnetic field from that, didn't I? That was silly of me. Throw a magnetic field in there somewhere. If I can get my pen to write. Okay, put a B in somewhere in there. Okay, so grab the calculator. The area is 0.05 times.
I'm glad you get the area as 0.05.
I haven't got.
Oh,
The area is 0.05 times 0.08, which is 0.004, because it's a rectangle. And then the magnetic field is 0.25, and the current is 6.7. 0.0067. What's the magnetic moment of the loop? Honestly, don't remember. I believe the magnetic moment is has cosine in it. But I don't actually remember. Okay, apparently it's just divide by B.
divide what by B?
Divide part A by B. So it's just do what we just did, but don't use the B. So divide by 0.25, 0.268. And the maximum torque that can be contained with the same length of wire, same current in this magnetic field, well, the angle's already 1. That's the biggest it's going to get. So the only thing you could do is change the shape of the wire. So if instead of having a 5 by 8 rectangle, if we made it into a square, you would have bigger area. So that's 13 divided by 2. So 6.5 would be the sides of that square. So if I went 0.065 squared, that's the area, and then times the magnetic field, and times the current. Oops. I shouldn't have a decimal place there. So lop off a 0, so 0.0070, 0.0071. Okay, let me do it again. All right, is 6, yeah, that really is 0.065 squared times 0.25 times the current, 6.7. 007.
But here's my question.
What's your question?
5 times 8 is 40, right?
Mm-hmm.
6 times 6 is
Well, 6.5 times 6.5.
still gonna be smaller than 40.
It's 42.
Oh,
Times 0.25 times 6.7. Okay. I'm tired. This has just been a weird morning. Now times speed times. Oh, that was silly of me. The most torque is not when you do a square. It's when you build the wire into a circle.
okay.
So the circumference of, or the perimeter of that square is 26. Divide that by 2 pi to get the radius, and then
Okay.
build a circle out of it. Okay, yeah, that was just ridiculous. So it's a little early, but I don't know.
0.009.
This is one of those days when